Hello students, in the last section we have discussed about the Poisson's equation and the Laplace equation, and also we have seen that how to derive the Poisson's equation and Laplace equation. So actually the Poisson's equation and Laplace equations are meant for the solving the boundary value problems, because for we are knowing the potential and the voltages at the boundary values only. So by using those potentials at boundary, so we are going to find out the potentials for whole field. So therefore the Poisson's and Laplace equations are used, right? So now what we do is we consider this Laplace equation, and we can use this Laplace equation in all three coordinate systems. So let us see the Laplace equation in all the three coordinate systems. So Laplace equation in three coordinate system. So first one we'll see about in Cartesian coordinates. So already we know that we are having the equation for del v. Already we have derived in the this equation, potential equation, using the del operator. So that is nothing but equal to dou v by dou x unit vector ax plus dou v by dou y unit vector ay plus dou v by dou z unit vector az. So this is equation for potential, right? Now if you want to have the equation for vector field, that is A, so we have the equation of del of A is equal to dou of ax divided by dou x plus dou of ay divided by dou y plus dou of az divided by dou z, where ax, ay, az are the components of the vector field A, right? Knowing already we know that previously we have derived about the Laplace equation. So there we are knowing del square v is equal to, we can write it as del dot del v. So hence we can write the Laplace equation as del square v is equal to dou square v by dou x square plus dou square v divided by dou y square plus dou square v divided by dou z square is equal to 0. Hence this is the Laplace equation in the Cartesian coordinate system, where we can use to solve the problems if the voltage potential function is given, right? So evaluating it to 0, we can estimate the potential. That is nothing but we can satisfy the Laplace equation, right? So now next we see the Laplace equation in a Cartesian. Already we have gone through Cartesian. So next we see the about cylindrical coordinate system, right? So here is the cylindrical coordinate system. In cylindrical coordinate system we are having the equation for potential, that is in terms of del v, that is nothing but dou v by dou rho a rho unit vector plus 1 upon rho dou v by dou phi a phi unit vector plus dou v by dou z az unit vector. This is the equation for potential, right? And if you want to have a dot product of vector field, that is del dot a, so we can have this equation as 1 by rho dou by dou rho into bracket rho of a phi a rho plus 1 by rho dou of a phi divided by dou phi plus dou of az divided by dou z. So this is the equation whenever we use the vector field. Now already in the previous in the Cartesian, how we evaluated for Laplace equation, so same it is evaluated for cylindrical coordinates, right? So del square v is equal to del dot del v we can write. So hence the Laplace equation is del square v is equal to 1 upon rho into dou by dou rho into bracket rho dou v by dou rho bracket complete plus 1 upon rho square dou square v divided by dou phi square plus dou square v divided by dou z square is equal to 0. So this is the equation for cylindrical coordinate system. If the potential is given and it should be evaluated in cylindrical, we can use this equation. This is the equation for Laplace equation in terms of cylindrical coordinate system. Now next we see the Laplace equation for spherical coordinate system, right? So in spherical coordinate system we are having the equation for potential, that is del dot v is equal to dou v by dou r unit vector ar plus 1 upon r dou v by dou theta a theta unit vector plus 1 upon r sin theta dou v by dou phi a phi unit vector. So where in spherical coordinate system r, theta, phi are the parameters, varied parameters, right? Now if you want to consider for vector field A, so del dot A is equal to 1 upon r square dou by dou r into bracket r square ar plus 1 upon r sin theta dou by dou theta into bracket a theta sin theta plus 1 upon r sin theta dou a phi by dou phi. This is in terms of vector field. Now knowing del square v is equal to del dot del v, we can have the equation for Laplace, that is del square v is equal to 1 upon r square dou by dou r into bracket r square dou v by dou r plus 1 upon r square sin theta dou by dou theta into bracket sin theta dou v by dou theta plus 1 upon r square sin theta dou square v by dou phi square is equal to 0, right? So this is about the Laplace equation for all the coordinate systems. Thank you.